In today's class, we'll be talking about magnetic circuits. We will be doing a simulation with finite element methods so that we understand how the circuit works, what materials are used in magnetic circuits, and what are the properties of those magnetic circuits. We will do the simulation because we cannot do the real experiments in the class. And in the simulation we will see similar effects, for example as force in an electromagnet, as we would see in a real lab experiment. For those experiments in simulation, we will use an open source simulator called Finite Element Method Magnetics, which you can download on this website. So I will first show you how to use this simulator so that we can create a magnetic circuit. Now please note that this tutorial will not be a complete introduction to finite element methods. In order to understand how those method works, you should read the manual, or you should take some classes in mathematics, for example numerical mathematics, where they will explain you how those element works. In this tutorial we will use this as a tool to visualize the magnetic field, and we will not go any deeper into what's happening behind this visual appearance. So if you open the software called FEM that you have installed, you need to define a new project. So I will select a new project, and now we need to define what do we want to solve. This software is able to simulate 4 problems. It can simulate magnetic problems, electrostatics, it can do heat flow, and it can simulate current flow. In this tutorial we'll be talking only about magnetics, so we'll select the magnetics problem. Now this software works in 2D, so what we will be drawing is a cross-sectional view of our circuit. So for example, if I select an example from our lab manual, we see a circuit that we would like to simulate, and I will prepare a very similar circuit to this one. So what do we see here? Here we have a magnetic core. This core is from ferromagnetic material. In this case it's using M36 steel. Here we have a coil with a given number of turns and a given current and given material. This will be copper. And here we have an air gap in the magnetic circuit. So what we want to simulate is what is the magnetic flux in this magnetic core and how is it going through the air gap. So the result that we will see is similar to the one we see on the right here. The coil will create the magnetic flux. The magnetic flux will be guided through the iron core, or steel core in this case, and it will go through an air gap. And if we have, for example, here another material, we can study what are the magnetic properties of this material. So let's create a similar circuit in the FEM simulator. Remember that this is a 2D problem, so we first need to define what will be the depth. So I will go to problem, and here I am solving a planar problem. My units are millimeters. You can switch also to other units if you need it. We will solve this only at DC right now, so we're working with DC current with frequency 0, and the depth is the depth of my material. So I will simulate, for example, a magnetic circuit that has the third dimension of 50 millimeters. Now that we have the problem defined, we can set the grid in which we will be working. So let's go to grid and let's set some units so that at the end we have some nice straight lines in our circuit. So I will set my grid, for example, to 1 millimeter. We can see that now the grid has changed, and I can of course zoom in and zoom out with those buttons on the left side. And now this grid is 1 centimeter and the smaller grid is 1 millimeter. And as I want to have like nice straight lines in my drawing, I will snap all my points to this grid. Now I need to define the geometry of my circuit. So I will do something that's called a C-type core. It resembles the letter C. Here I will select the points and I will draw the points that are on the edges of my core. So points are selected. Now let's do it, for example, like this. I will plot the outline of my core. Note that I will use a core which has a constant cross-section. So here I will use the grid of 2 centimeters to define my cross-section of the core. And my core will look like this. So here I will have a small air gap, let's say like that. And now this will go over there, 2 divisions and 2 divisions here, and I'll just finish the core drawing. So now I have the points on my edges, and I can switch to lines and I can connect my points together. Of course, if for example you have a drawing in AutoCAD, you can import this drawing into the software by using the menu here, import DXF, and then you can import directly your drawing from some file. On the lab class you will draw just a few cores like this, and then we will give you the remaining files so that you can directly use them and focus on the magnetic circuits and not on drawing the actual circuit. So this is my core. You can see it has a letter C shape, so it's called C core. Now I will add my coil, which will sit around this part. Remember that we are in a cross-sectional view, so I will plot the coil as it would be 1 on the left side of my core and 1 as it would be on the right side. Again, it should be symmetrical, so I have tried to make those 2 sections. Now you see I did not align that properly, but that's definitely not a problem right now for our simulation. We just want to see how the software works. So this should be a nice rectangle, and hopefully this will be a nice rectangle as well. You can of course delete the points. When you select the points, you right click on them. Now it is highlighted in red, and then you press delete and it deletes the point and eventually also the lines. So what you can do is you can go back. You can of course zoom in so that you can make a better picture. So that's what I will be doing. So here I will define my 2 new points and I will make a nice rectangle in my coil. So now we have our coil and we have our core, and we need to define also the external boundaries of my simulation so that we tell the software in which area it should actually simulate the magnetic field. So for this you may use a boundary which may be rectangular around or maybe circular. I will make a rectangular boundary. It does not have to be very wide, but I will just select something like this. The width of your boundary actually depends on the shape of your magnetic core that you're solving and on the magnetic flux. But if you make it larger, it will have an impact on the calculation time. For this specific problem, it is not an issue because we have a fairly simple geometry, and therefore our mesh at the end will be quite small and the calculation will take about a second. But for more complicated problems, it may take a few minutes or maybe even a few hours if you have like a very complicated simulation. So now we have our geometry defined. We now need to define what materials will be used in the simulation. So for this we go to Properties, and here we have a Materials library, and I can drag the materials from the library into my model. So I will definitely use air. I will use a soft magnetic material, silicon iron, and for example I will use M36 steel. This is a special silicon steel with a quite high content of silicon, which has special magnetic properties. And the third material will be copper, and let me use for example a copper wire, which we have here in copper metric magnet wire. So this is copper, and for example let me select 0.4 millimeters. That's the diameter of my wire. Before we drag our materials into the library of our model, we can of course examine the properties and see how they are defined in the library. So for example, let me open the M36 steel. We simply double click on this material. We see how it is defined. So we see that it is defined with a nonlinear BH curve, and that it has some defined properties. We can even edit the BH curve and take a look on the BH curve in a plot. So let's take a look. So here we have the values. We may eventually edit them. You may use your own material if you have some data. And here we can actually plot the BH curve of this material in the library. So we see that this is a non-linear material. This is quite typical for ferromagnetic materials. They first have a fairly linear region where the magnetic flux density depends on the current in a linear fashion, and then in this region they are saturated, and they change only slightly the value of B if you are increasing the current density. So this is a typical behavior of ferromagnetic material with saturation. I will add a fourth material in my model so that we later see also the effects of those linearities and non-linearities. So for example, let me select some iron from the library, and let's select for example, say normal iron. Here we have for example pure iron. So I will just drag it into my model so that later we can actually see the differences with different materials. Now for the pure iron, if you see that, you see that this is defined also as a nonlinear BH curve, but you may find that other materials may be defined also as linear materials. So be careful about this selection and verify that your material is defined correctly. or in other words, that your material is doing what you are expecting it to do. Because, for example, if you select a material that has a linear dependence, for example, if for some reason you would change this to linear relationship, you may get the results from the simulation that are completely unrelated with reality. So it's always a good practice to check what properties of materials do you have, and if you have, for example, your own material, then define your own material if you want the simulation for your own material. So now in our model we have added those 4 materials. We now need to define those materials for our areas here. So here we use this button, which is to operate on block labels, and we will define the block of my material. So I will have one material, for example, here, one material will be there, third material will be there, but this will be copper, so it will be the same, and here everything else will be air. Now we need to define one last thing before we add the materials. We know that here will be an inductor with some current. So we need to define a circuit, and we need to define the value for our current. So if we go to properties and circuits, then here we can define our circuits. Currently we don't have any circuit defined, so I will just add my circuit. I will name it, for example, coil, and I will set what is my current. So for example, 1 ampere. And now we have everything defined, and we can start setting our materials and circuits. So I have still selected this operate on block label. I will right click on my material, it is highlighted in red, and now I will click on properties of the selected entity. That's this icon over there. We can open it, we can select what is the block type, and this will be my steel. That's all. So just define the material. Here we will use the same. We can also, of course, use the menu here. So we don't need to use this icons, but we can use the menu here on top as well. So here let's define that this is air, and for this I will need to define that it's copper wire, and that it is a part of my circuit. So again, right click, select properties. Here I will select the 0.4 copper wire, and here I will add that this is a part of my circuit that I have called coil. This is giving me the current, and here I need to define the number of turns. The software will not check if your number of turns will really fit into your window here, into your rectangle. So again, that's another reason why you need to think about what you're doing, because you can easily put 10,000 turns, but in reality you are limited in this available space, and the wire diameter will give you only a specific number of turns that you can mechanically fit into this window. So I will use, for example, 100 turns in my simulation. And here we need to define the same. So again, let's click on the properties. Let's select 0.4 copper wire, the same circuit, but now here we will use the same number of turns, but remember that this is a cross-sectional view. So if the current is flowing, for example, in this right rectangle into the direction of my plane, then here on this second part of the coil it is flowing out from the plane. So I need to add minus 100 turns. And with the sign I can tell what is the positive and what is the negative direction of the current that flows in the coil. So now we have everything set up, and we can create the mesh for calculation. So again, you can use the mesh menu here, or you can use the icons with this icon on the top button bar. We'll run the mesh generator. We'll need to save the file first, so let me save this as, for example, E1, let's say, and I will create the mesh. Now by default the mesh is created automatically. You can of course adjust the precision of your calculation and the number of nodes in the mesh. Now how is the finite element method works? You see those triangles, and in every triangle we create a set of differential equations that describe the magnetic field. So in total we have, right now we have like about 6,000 nodes here. So in total we will need to solve a few thousand of differential equations. But on a computer it's quite fast. So now that we have defined the mesh, what do we see here? We see that the mesh is finer around the edges, because we can expect that the accuracy required around the edges will be higher than, for example, here when we have solid material. So the software has automatically accounted for that and made a finer mesh around my edges. Now we can run the calculation. Again, we can analyze it with the menu, so let's do that. Let's analyze that. Now it will calculate the result. Sometimes it takes few seconds, sometimes it's like quite fast. Now this is the first time I have run today the software, so it took a little bit longer before it started. Now it's completed, and we can view our result of the analysis. So here we can see the magnetic field in our magnetic core. This is the density plot of magnetic flux, and here on the scale we can see the values in Tesla of the magnitude. Of course, this will be a function of the current in my set coil and of the number of turns, and of course of the materials. However, we can see here the flux lines. We can see how the magnetic flux is flowing in the magnetic circuit. We can see how it is going through the air gap. And we can also see that, for example, here we have a very low value of the flux density. So this means that here we basically do not need that material, because all the magnetic flux is flowing basically here, like that, and here the flux density is much smaller. So we could also optimize the design in terms of mechanics, so that, for example, here we round the edges and we make it lightweight, and we don't need that much material. Let's zoom in on the air gap. Here the air gap is basically what is determining the properties of our magnetic circuit. So we can see that the flux lines in the middle of the air gap, they flow like that in the vertical direction, which is perpendicular to the air gap. And as we are going near the edges of the air gap, the magnetic flux starts to flow like that, which means that it's not flowing in the air gap, but it's flowing outside somewhere. And if, for example, this would be an electromagnet, then we try to maximize the field lines and flux density in the air gap, and we try to minimize what's basically a loss, and that's all those magnetic flux lines which are outside. So this would be a stray magnetic flux. It would be lost and would not do what we want to do. We can see here the values of flux density. So here on my scale, the maximum is about 0.4 Tesla, which is still fine for this material. It will not be saturated. And we can see that the maximum flux density is in the corners of my design. So if I zoom in on the corner like that, we see that this corner would be the place where the material would be saturated in the first place. So if we increase more and more the current, then this would be the point where it starts to saturate. We can take a look if this will really happen, or what will be the effect of this. So let's keep everything the same number of turns. Let's just increase the current in the coil. So I will change the properties of my circuit here, of my coil. I will just modify it, and now instead of 1 ampere I will enter 10 amperes. So we have 10 times higher current. Let's run the calculation again. Let's see the result, and now we see that it's fairly different. I've increased the current 10 times. We can see that now this spot has grown much bigger, and that we are now about 0.9 Tesla. Now this material, the M36 steel in my model, includes saturation. So it will saturate at the point where no more magnetic flux can basically flow in my circuit. But if you select a material that has a linear dependence, it may happen that you may get results from the simulation that are completely unrelated with reality. Because ferromagnetic materials in reality have some saturation point, and you need to take this into account if you're designing such a magnetic circuit. Let's see how we can read our values, for example, for the flux density that we have here in the air gap. So we can switch again to points, and we will measure the value of flux density at some point. So for example, let's click here, and now in this output window we see that at the point that I have just selected, the flux density, the magnitude of it was about 0.41 Tesla. Again, we see here the effects on the edges where it starts to get saturated. It's saturated more than the material here. If, for example, I select the point, let's say here, outside of my magnet, here we see, okay, 0.046. So we can see that basically all magnetic flux in our circuit flows inside of my magnetic core, and there is some magnetic flux outside as well, but it has much smaller magnitude. Several orders of magnitude smaller is the magnetic flux that flows outside. And here we see a quite nice effect. Here we see that this would be the stray magnetic flux. It's not in the air gap, but it is around the air gap, and it would not do the proper work as we want to use it in our magnetic circuit. So let's now take a look on how we can use this simulation, for example, to calculate the force on an armature of an electromagnet. So let's see, we will provide you the files so that you can already open and you don't need to draw the geometry. So let's open, for example, this problem. Here we see that this is an EI core. This has a shape of letter E, and this has the shape of letter I. This would be the armature of the electromagnet, and it would be attracted to this E core. And here we have a small air gap. Now my dimensions are roughly 1 millimeter. We have defined the number of turns and all the materials. So let's just run the simulation. You see that now I have created my mesh. I will run the calculation and I will display my results. Here I am using a larger value for the turns and for the current as well. So we have about 1.8 Tesla maximum flux density in the core, which is at the higher limit of this material. And we can see that the flux lines, they go nicely through the air gap. Let's see how we can plot a chart that will tell us what is the flux density here in the air gap. So for this I need to define a line that will be used to plot the flux density. So I will just go back to my drawing. I will zoom in to my air gap like that. I will add some points and I will add a line, and we will plot the dependence of B along this line. I will just run the calculation again, and if I plot the result now, here I have my line. I will have to select the 2 points on the edges. Now you see my line is highlighted in red, and I just can use this plot function and select what do I want to plot. So I want to plot the magnitude of flux density. You can export this into a file and then, for example, plot that in Excel. Let's do that, and here we see the plot. So we see that in the air gap we have a fairly constant value of flux density, 1.5 Tesla, which is quite fine. And outside of the air gap the flux density is sharply decreasing. So outside of the air gap we have small flux density, and inside we have a fairly constant flux density. And that's exactly what we see here from our color chart. Now keep in mind that this is a simulation. If in reality you need to calculate some believable results, you always need to calibrate your model with some experiment. So do some measurements and verify the calculation at least at some points. And then after this calibration of your FEM model, you may say that it gives you believable results. So this is how to plot the flux density. And the last thing that I will show you is how to calculate actually the force that is being created on this armature and that is trying to drag the armature upwards. We need to select a block. Here this is this green icon. Again, you can do this with the menu. You can select an area and do the operations on the areas. So now I have selected an area. This will be my area that I want to use, and we will now calculate the integral of this properties of my block, and from the options we will select force via weighted stress tensor. Now if you would like to know how this method works, the FEM site has fairly good manuals that explain how the method works also in mathematical perspective. But as I was saying here, the purpose of this tutorial is not to learn what's behind the FEM methods, but to use this as a tool so that we can play with the electromagnets, and we can later use this knowledge to understand, for example, electric motors. So now I have calculated my force, and we can see, okay, it's 52 newtons. So the pulling force is about 5.2 kilograms approximately. And we can see how this will vary with the current. We can of course expect that if I decrease the value of my current, it will decrease the force. So let's see that. Here, open the properties of my circuit. You can see I have used 1 ampere in my simulation, but I have used about 66 turns. So let's decrease that 10 times. So let's point 0.1 amperes in my current. And just run the simulation again. Let's see the result. Now we see that we have different magnetic flux density that's visible directly on the scale. And here, if I select operation on areas, I select the armature and calculate the block integral and calculate force. We see that now we have 1.5 newtons. So I have decreased the current 10 times, but now the force has decreased about 40 times, because we had 50 newtons, 52 I believe, and now we have 1.5. So the dependence of force on current is nonlinear. That will be one of the tasks that you will do on the labs, to plot that dependence. And moreover, it will also be a function of the air gap. So let's now see how we can actually move the objects in this simulator so that we can move the armature closer and further. So what I will do is that I will just delete my line here, because I don't need it anymore for the flux density. And now I will select all this armature and I will move it a little bit closer to my electromagnet. So I will now be in the segment line mode, and I will select the group of my entities. So I will just select this, and now I can move it, not with the mouse but with the menu. So here you can see I have a way so that I can move my magnet, and we want a vertical shift, and let's move it, for example, by 0.5 millimeters. Now this is a lot, so this is too much. So I will go back and I will move it. Again. I believe that in my model somewhere I still have the units of inches in as for the movement. So what I will do is that I will move it vertically by 0.01, for example. Now see, that is fine. We have a much smaller air gap. So what we expect is that now we will have a much larger force than previously. Let's try that. Let's run the calculation, and let's see the results. We see that we have a slightly larger value of flux density, because now the air gap is smaller and we have a much lower magnetic reluctance in the circuit. And let's see the force. So let's see here, force, and what's the result? We see 12 newtons, not 13 newtons. So I kept the same current, I kept the same number of turns, I decreased the air gap size, and now from 1.5 I have about 13 newtons. So there is also a quite non-linear dependence between the force and the air gap size. So what you will now do on the lab is that you will be given individual assignments, individual values for currents, air gap size, and number of turns, and you will simulate the circuits, and you will plot the dependencies between forces, flux densities on all those variables.